Solving exponential equations. An exponential equation is an equation in which the variable appears in the exponent somewhere. So here's examples of exponential equations. 10,000 equals 3,000 times the quantity, 1 plus 0.035 divided by 12, all raised to the 12y power. The y's up there in the exponents. 3 equals 5 to the x. X is in the exponent. 1/2 to the m power equals 11.3. M is in the exponents. These are examples that are not exponential equations. Y here on the left is nowhere in an exponent. It's just a factor on the left. So 10,000y equals 3,000 times the quantity 1 plus 0.035 over 12 to the 12th power is not an exponential equation. 3 equals x to the 5th. X is the base. X is not a variable that's in the exponent. It's in the base. M to the 1/2 power equals 11.3. M is again the base. So to solve exponential equations, we must remove the variable from the exponent. How are we going to do that? We're going to use a lot of the properties we've already seen. If we can write both sides with the same base, we must use the equivalency property of exponents, which says if base a to the x power equals base a to the y power, then intuitively x must equal y. So for example, to solve 25 to the x power equals 1/5, we want to write both sides with the same base. So let's choose to write them with base 5. So we're going to write both sides with the same base, and then once we do that, we're going to set the exponents equal to each other. So working on the left-hand side, 25 is 5 squared to the x power, and 1/5 on the right-hand side would be 5 to the -1 power. So we're going to simplify the left-hand side. We'll get 5 to the 2x, because a power raised to a power is just the product, 2 times x. And we didn't have anything to do on the right-hand side. So now, because we have the same base raised to the power on the left as the same base on the right raised to a different power, those two powers, those two exponents, have to be equal. Now we have just a linear equation to solve. We're going to divide both sides by 2, so we get that x equals -1/2. But if we cannot write both sides with a common base, we must use logarithms to bring the variable out of the exponent. We may use the following equivalency property of logarithms to do so. If m equals n, then log base a of m must equal log base a of n. So we can take the log of both sides. For example, 25 to the x power equals 1/6. Well, I'm not seeing how I can get 25 and 1/6 to the same base. So I'm going to take the log of both sides. I'm going to say log of 25 to the x power equals log of 1/6. I'm going to do the same thing to both sides of the equation to preserve equality. Now I can do what we've done in previous videos. I can take this power and bring it down as a factor in front. So I have x times log of 25 equals log of 1/6. Now I have a linear equation. Remember, log of 25 is just a number. The exact value is log 25. We could estimate it with a calculator. So I'm going to divide both sides by log of 25. So x would equal log of 1/6 divided by log of 25. So if you were to use a calculator, you would just do log of 1/6 divided by log of 25 to get an estimate of what that would be. It would approximately be equal to negative 0.5566. Or we could do this with LNs, because most of our calculators also have the natural log, and the process is literally the same. It's just that we're going to use the natural log. So we'd have x ln of 25 equals ln of 1/6. We would divide both sides by ln of 25. So we get x equals ln of 1/6 divided by ln of 25. And if we brought up the calculator again, we would get exactly the same approximation. Just remember that what I just boxed in there, ln of 1/6 divided by ln of 25, or log of 1/6 divided by log of 25, are exact answers.